Okay, so now that we have seen a little bit about this circuit, how it actually works, so let's go and take a look at the. So you see over here, so you see that my input voltage was somewhere about 19 volts all throughout this experiment. 19 volts peak to peak. This was my input voltage, and this is my frequency, goes 10 hertz, 770, 1.27 kilohertz, and goes all the way up to 205 kilohertz, all the way up to here. And my output starts from 14 millivolts and goes all the way up to 100 millivolts here, 220, 800 millivolts, around 1.3 millivolts here, and 2.7 millivolts at 200 kilohertz. And then the rest of the way I have noted down some values here. For example, at 400 kilohertz, the output is at about 5.3 volts peak to peak, and then at 800 kilohertz the output is at 12, and at 1.3 megahertz the output was about 19 volts peak to peak, which is my full supply voltage. And then from this point onwards the output started diminishing. So if I were to do a quick graph of voltage versus frequency here, I will do it like this. Okay, so I have to go from, let's say that you go from 1 megahertz, so that's 1 million. So this is your F of in, this is your V of out, and this is 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20 volts peak to peak. Okay, so this is 2, 4, 6, 8, 10, 12, 14, 16, 18, and then here you are at 1.3 megahertz or so. Right here you're at about 1.3 megahertz, so that's about 1.3 megahertz. Okay, so the important points here are about 400 kilohertz, so you can go for example, basically, I don't know, 10, for example, 100, 1,000, let's take this as 10,000, let's take this as 100,000 kilohertz, and this is I'm sorry, 100,000 hertz, and then this is 1 million hertz, which is 1 megahertz, and then this point over here, let's take it as 10 megahertz, okay. So over here the voltage was at 10 hertz. The voltage was at 14 millivolts, meaning that 14 millivolts is the same thing as 0.014, so very close to zero. Very close to zero. At 20, at all the way up to what was we were doing at 100, it was about 1.3. 1.3 would be somewhere over here, and at 1000 it was the same thing all the way up to 205 kilohertz. So at 200 would be somewhere over here, and that's 2.7, around somewhere over here. And then at 400 kilohertz we are at 5.3 volts. 5.3 volts would be at 400, would be somewhere over here, and at 800 kilohertz we are at 12.5 volts. So 12.5 would be somewhere over here, and then we are at 800 kilohertz, 12.5 volts peak to peak. 12.5 volts peak to peak would be somewhere over here, and then at 1.3 megahertz we are at 19 volts peak to peak. So 19 volts peak to peak, 1.3 megahertz. So this is 1 megahertz. So it would be somewhere over here. Okay. And so your graph is basically looks something like this. Must be somewhere over here. Looks something like this, all the way up to 1.3 megahertz. This point over here is at 1.3 megahertz. And at this point, it kind of keeps decreasing. Okay? So that's basically how this circuit works. So what that means is that if you want to work with this circuit, for whatever reason, after 1.3 megahertz, of course this frequency this point must depend on the value of the inductor that you choose. I don't even know what this point is called. Whatever that is called, it doesn't really matter. Whatever it's called, it doesn't matter, but I think that based on any sort of inductor value that you might choose, that you will get this point for any sort of inductor. And then you need to specify this point for any sort of inductor that you choose in your circuits. And then if you want to, then and then of course you know how your circuit works. You know that all the way up to this point you go all the way up to somewhere around your supply voltage, and then you keep falling down on the other side. So that's basically how this thing basically works. Now, what I want to do now is do a couple of basically calculations, and then we will end this thing. So for example, and you can go all the way up to 1.3 megahertz also, not higher than that. because our formulas after the 1.3 megahertz, our formulas actually will break, so we cannot use them there. But let's say, for example, for this point, I think for this frequency, for if frequency is equal to 802 kilohertz, if your V of in is equal to 19 volts peak to peak, and V of out is equal to 12.5 volts peak to peak, and your L was actually 110 microhenry, and the resistor that we used was 990 ohm. $110 microhenry. I think that's the right value. So that's basically that. So now, in order to learn, and then the circuit that we had was basically this thing over here. It was a high pass filter, meaning that you have a resistor over here, and this resistor comes into an inductor, and this inductor goes to ground. This is your V of out, this is your V of in, and this is your R, this is your L, and so that's basically, if you want to, let's say that you want to calculate the output voltage across basically the V of out over here, which is actually V of L as well, because you're measuring the voltage across this inductor. So your V of out is going to be equal to the value of this, the reactance of this inductor, which is X of L, the same thing as the resistance of this inductor. It's called reactance in this circuit, divided by the total resistance in this circuit, which is in this circuit is called impedance Z times V of in. Okay, so that's simple. And your X of L is equal to 2 pi FL, and your Z is equal to the square root of X of L squared plus R squared. Okay, so we can calculate X of L first, and then get to Z, and then put everything in this formula here. So X of L is equal to 2 pi times the frequency, which is times 802 times 10 raised to power 3 hertz, times L, which is 110 microhenry. So 110 into 10 raised to power negative 6 Henry. So you can simplify this a little bit. So 10 raised to power negative 3, and then you have 2 pi times 802 times 110 into 10 raised to the power negative 3, which is equal to 441, which is equal to 4411 by 25 pi. Okay, that's your X of L. And if you want to, an approximation to this would be 554.3 ohm. This is in ohm. This is approximately 554.3 ohm. So that's the resistance of this inductor at this frequency. Now your impedance over here is equal to the square root of X of L squared plus R squared. So X of L is equal to this value 4411. It's always better to use such values rather than the rounded values. 441 pi over 25 whole squared plus r squared, which is 990 squared. Okay, and then calculate this, the square root of so 4411 pi over 25 squared plus 990 squared is equal to 1134.6 is equal to 1134.60. So now your V of out is equal to basically this formula here, x of L by Z times V of in. So x of L is equal to this value, which is 4411 pi divided by 25 divided by Z, which is this value 1134.6, and multiplied by V of in, which was 19 volts peak to peak, and that's equal to 4411 pi over 25 times 1134.6 times 19, and that's the same thing as 4411 pi over 25 times 1134.6 times 19, which is equal to 9.28, 9.3. 9.3 volts peak to peak. Now the value that I got at this point was 12 volts peak to peak, but I think the frequency that I'm using is a little bit off, so I actually did not expect to get the exact value here. I can use some other point, which is really not necessary right now, because we have enough calculation we have many exercises at the end of at this point. We can go through those exercises, but just for the sake of basically for the phase shift, I want to know if I read the phase shift right. I'm pretty sure I did, but I just want to calculate the phase shift here. And to calculate the phase shift, you need basically your phasor diagram, and and the phasor diagram, what it is, okay, so the phasor diagram is, in the case of these RL circuits, is basically you have this V of L over here, and you have this V of R over here, and basically your I is along the same line, and then you have V of in, you have V of in over here. That means that if you are watching the voltage across the inductor with respect to the voltage, the input voltage, your inductor voltage is going to lead basically by this angle over here, and let's call this phi, for example, and let's call this angle theta. Okay, so now you know that V of basically tan of theta here, for example, tan of theta would be equal to this thing over here, basically opposite to adjacent, so that would be V of L to V of R. But there is one more way to calculate this, which is x of L to R, which is, I think I forgot. I did. No problem. Okay, So there is one more way, so that is x of L to R, or basically you know that x of L is the same thing as 2 pi FL to the same thing R. Okay, so there are these three ways to calculate this angle theta, and then since we are concerned about this angle phi here, then we can add these two angles together. I mean the sum of these two angles is 90 degrees. That way we can calculate these angles. I mean the other angle. Okay. So but first you need to calculate theta. Now you need to, for that I'm going to use this relationship here. So I'm going to use tan of theta is equal to x of L to R basically, and x of L is equal to 2 pi FL to 2 pi FL, and the frequency at which I basically measured the phase shift was 571 kilohertz. F was 571 kilohertz, and at this frequency the output V of L leading with an angle of 61.71 degrees. That was what I read. Okay, so since this was the case, now x of L at this frequency, so your x of L is equal to 2 pi FL, so 2 pi F was 571 kilohertz times 10 raised to power 3 hertz times L, which is equal to 110 microhenry into 10 raised to power negative 6 Henry. You can simplify this a little bit. 10 raised to power negative 3, and that would be equal to 2 pi times 571 times 110 into 10 raised to power negative 3, which is equal to 6281.50 pi. Okay, times divided by 50 pi. 394. Oh, I'm not sure if I did that right. 2 pi times 571 times 110 into 10 raised to power negative 3. 6281. That's the same thing as 6281 divided by 50 pi, which is approximately 394.6. 394.6 ohm basically. Okay, so now my tan of theta is going to be equal to this thing divided by R. So this thing divided by R is equal to 6281 pi divided by 50 over 990, which is the same thing as 6281 pi over 50 times 990. So if you do this, you will get 6281 pi over 50 times 990, which is equal to 0.39. Oh, sorry. Okay. So that is tan of theta. That is tan of theta. So now theta is equal to tan inverse of this whole ratio here. So so then you need to calculate tan inverse of 6281 pi 50 times 990. If you calculate that, first the other way around, you will get 21.73 degrees. You will get 21.73 degrees. That means that your theta here, theta is equal to 21.73 degrees. So since theta is equal to 21.73 degrees, phi is going to be equal to, so you know that phi plus theta is going to be equal to 90 degrees. So now your phi is phi plus theta, and theta is equal to 21.73 degrees is equal to 90 degrees. So phi is equal to 90 degrees minus 21.73 degrees, which is equal to 90 minus 21.73 is equal to 68.27. 68.27 degrees. And that is basically the angle that we got there as 61.71 degrees. 7 degrees off, but you can expect to have that reading on an analog oscilloscope. I think digital oscilloscopes do that automatically for you, but well, we don't have it right now. So that's basically all about these circuits. And so in the next video we will do a couple of exercises related to these circuits, and then we have some other material to cover here. So I'll see you in the next video. Thank you.